A very good morning to all of you. So I cordially welcome you all for this engineering thermodynamics course. So the today's classroom discussion topic is a Carnot cycle, and what is the motivation why we have to study this Carnot cycle. So here I have given you. So it is very essential to know that why Carnot cycle considered as an ideal cycle in thermodynamics and why it is impracticable in the actual practice. So this particular lecture is having two outcomes. So I'm expecting after completion of this lecture, so you should be able to draw the Carnot cycle on PV diagram and also on the TS diagram and derive the efficiency of the Carnot cycle. And the second outcome is you should be able to solve some problems on the Carnot cycle. So now let us see. So what are the various processes are there on the Carnot cycle and how can we draw the schematic diagram on the PV diagram as well as a TS diagram. So let us consider this particular the PV diagram. So whenever you are going through the PV diagram and the TS diagram, so it is very easy to remember the Carnot cycle on the TS diagram because just we are drawing something like a rectangular box. So a rectangular box on the TS diagram, it is very easy to remember the Carnot cycle rather than on the PV diagram. Because on the PV diagram, just you are able to see there are so many curved lines are there. So whenever you are drawing all these types of the four different curved lines, so it is very difficult to remember the Carnot cycle and the PV diagram. That's why I am suggesting you to please remember the Carnot cycle better on the TS diagram because it is simply drawing a rectangular box. So whenever I am saying that it's a rectangular box, because 1 to 2, that is the horizontal line. The horizontal line on the TS diagram is basically representing it's a constant temperature process. That is whether it is the 1 to 2 process or the 3 to 4 process. So these two are basically carrying out according to the constant temperature process. So that's why these are known as the isothermal process, but we are assuming that it is taking place according to the reversible process. So these two are the reversible isothermal process. So the same thing here I have represented. So process 1 to 2 is a reversible isothermal because it is the expansion process is taking place. So the reversible isothermal expansion or heat addition, and 3 to 4 it exactly because reverse it is the expansion, so that's why it is the compression. So reversible isothermal compression process or the heat rejection process. So next you concentrate on the vertical lines. So 2 to 3 is a vertical line and similarly the 4 to 1 is also a vertical line. So the vertical line is basically representing it's a constant entropy process. So constant entropy process is nothing but it's an isentropic process. So 2 to 3 and 4 to 1, these are nothing but isentropic process. The another name for the isentropic process is the reversible adiabatic process. Isentropic, that is iso plus entropy. Iso means same and entropy, that is entropy will remain same or entropy will remain constant during the isentropic process. So that's why the 2 to 3 it is the isentropic expansion process, and similarly this particular 4 to 1, so sorry here not 3 to 4, it is the 4 to 1. So 4 to 1 it is the isentropic compression process. So basically here you have to remember what are the various processes are there in the Carnot cycle. That is the two reversible isothermal process and two reversible adiabatic process or isentropic process. So here this is a very important one, that is what are the basic processes are there in this particular the Carnot cycle. So that is whatever we explained through the PV diagram and the TS diagram. So here the same thing once again the illustrated very clearly according to the PV diagram. So now, why the Carnot cycle is not possible in the actual practice? So because our first lecture outcome is we have to represent properly the Carnot cycle on PV diagram as well as on TS diagram. Now, just now we have seen that is two reversible isothermal and two reversible adiabatic processes are there, that is on the Carnot cycle. That is why Carnot cycle is basically taken as is the ideal cycle in the thermodynamics. So why it is considered as the ideal cycle means because it is containing all four reversible processes. And in the previous lecture we studied that whenever we are having the reversible processes in a particular cycle, so that will give you the maximum work from that particular the cycle or the maximum efficiency which we are able to expect from that particular any cycle if it is operating with all four the reversible processes. So that is one of the reasons that why we are considering the Carnot cycle as an ideal cycle. So that is, it is basically consisting of all four reversible processes. So all those particular the four reversible processes are giving us the maximum efficiency or the maximum amount of the work output from that particular the Carnot heat engine. So that's why it is considered as the ideal cycle. So, but whenever I am saying that is the ideal cycle, so now it is not at all practically possible. So why it is not practically possible? So that is one of the reason is because I told you that the reversible processes cannot be obtained in the actual practice due to the presence of the friction and due to the electrical circuit. That is, I have already told you that there are the various reasons are there. So why all the processes are leading to the irreversible processes. The first reason is the presence of the friction, and the second one is heat transfer through a finite temperature difference, and like that we are having some number of the reasons are there. So why the reversible processes cannot be obtained in the actual practice. So the first one is, since it is containing all four reversible processes, that is the frictionless processes are not at all possible in the actual practice. So that's why it is very difficult to obtain in the actual practice. And the another important process here is isothermal process and adiabatic process we are having in the Carnot cycle. So under what conditions the isothermal process is basically carried out? So if you want to obtain the isothermal process, so the piston movement should be very slow. So that is, the piston has to be the piston has to be moved very slowly. And immediately what is the next process is the adiabatic process. So in the adiabatic process, the piston has to move very fast. So that is, one process is at extremely slower pace and the next process is at very extremely faster pace. So such variations in the engine so cannot be possible in the actual practice. That is, one process is extremely slower rate and the immediate next process is at immediately at the faster rate. So such variations are not at all possible whenever you are running any type of the heat engine in the actual practice. So due to all these particular reasons, the Carnot cycle is not at all practicable in the actual practice. And the next one is, how can we find out the efficiency of the Carnot cycle? So always we know that the efficiency is nothing but is the output by input, and in case of this particular the Carnot cycle efficiency, so it is nothing but output is nothing but work done, and the input is nothing but heat supplied. So work done is always equivalent to the difference of the two heat transfers, that is Q1 is nothing but heat input to the heat engine and Q2 is nothing but heat rejected by the heat engine. So W, that is the work done, is always equivalent to Q1 minus Q2, and heat supplied or heat input is nothing but is a Q1. So the thermal efficiency of an irreversible process, that is all the spontaneous processes are leading to only the irreversible. So the Carnot cycle efficiency, that is the actual Carnot cycle efficiency, is basically written as Q1 minus Q2 by Q1 or 1 minus Q2 by Q1. But sometimes you will say that the heat engine is operating on the Carnot cycle. So whenever it is operating on the Carnot cycle, then the Q2 or Q values have to be replaced by temperature. So 1 minus Q2 by Q1 can be written as 1 minus T2 by T1. It is nothing but T1 minus T2 by T1. So that is the Carnot cycle efficiency of the heat engine is T1 minus T2 by T1. So like that we are able to distinguish the irreversible Carnot cycle efficiency as well as the reversible Carnot cycle efficiency. So it is about the lecture outcome number 1. And coming to the lecture outcome number 2, so based on this particular the input, so you should be in a position to solve some problems based on the Carnot cycle. So that is a previous gate question based upon the Carnot cycle is, so the two Carnot engines work in series between the source and sink temperatures of 550 Kelvin and 350 Kelvin. That is, the T1 is given as 550 Kelvin and T2 is given as 350 Kelvin. Here I am assuming that the source temperature as T1 and sink temperature as T2. So T1 is equivalent to 550 and T2 is equivalent to 350. If both engines develop equal power, so that is the power produced by the two heat engines are same, that is the W1 is equivalent to W2. So then is asking us to determine the intermediate temperatures. the intermediate temperature. So that is very, very important one. So here you go through because based on this particular the problem, you should be in a position to draw the schematic diagram. So here we are saying that is a two Carnot heat engines are there. So that is here it is a heat engine 1 and here it is a heat engine 2. So heat engine 1 is operating between this particular T1 and T2 temperature limits, and heat engine 2 is operating between the T2 and T3 temperature limits. So in the problem he has given T1 value as well as the T3 value. Now he is asking us to determine what is the T2. So because the T2 is the common temperature for heat engine 1 and heat engine 2. That is T2 is the sink for the heat engine 1 and it is the source for the heat engine 2. And in the problem he has given that W1 is equivalent to W2, that is the work output by the both the heat engines are basically same. So with that particular condition we have to find out the intermediate temperature. So now you write down the efficiency for the first heat engine. So that is the efficiency 1 is equivalent to W by Q1, that is a T1 minus T2 by T1. And you know that what do you mean by the W? W is nothing but Q1 minus Q2. So Q1 can be written as Q2 plus W. And similarly, you write down the efficiency of the second heat engine, that is the T2 minus T3 by T2, because I told you that T2 is the source temperature for the heat engine 2. So T2 minus T3 by T2, so that will be equivalent to W by Q3 plus W, because here W2 is nothing but is a Q2 minus Q3. So Q2 is equivalent to Q3 plus is a W2 or simply the W, because he said that W1 is equivalent to W2 is equivalent to W. So that's why I'm taking the W is the common work output from the two heat engines. So just you simplify this particular equation and just you substitute what are the values of the T1 and T3. So here, because we are able to get, because whenever it is arranged in the series connection and whenever the work developed by the heat engines is same, so here one important conclusion you are able to derive, T2 is equivalent to T1 plus T3 by 2. That is, we are able to get the arithmetic mean. That is, always the intermediate temperature is equivalent to arithmetic mean when the heat engines are arranged in series and the work output is same, then the intermediate temperature is always equivalent to the arithmetic mean. So that is an important conclusion we are able to get it here. So T2 is equivalent to T1 plus T3 by 2. So automatically we are able to get the intermediate temperature is equivalent to 450 Kelvin. So like this we are able to solve some problems on the Carnot cycle. I hope you understood this particular the Carnot cycle concept, why it is treated as the hypothetical cycle or ideal cycle, and why it is not at all practicable in the actual practice. And already we solved some problems based upon the Carnot cycle. So thank you very much for listening this lecture on the Carnot cycle, and we will meet you once again in the next classroom discussion topic. Thank you one and all.